the stereochemical aspects of Sn1 and Sn2 mechanism. So in Sn1 mechanism, what is the stereochemical aspects? In the same way, what about Sn2 mechanism? First, we'll discuss one by one. Before discussion of this Sn1 and Sn2, you know what is the meaning of optically active halides? What is meant by optically active halides? Optically active halides is nothing but the halides which rotates plane polarized light. Which rotates what? Plane polarized. Towards right means clockwise direction. Towards left means anti-clockwise direction. So if it rotates clockwise direction, the plane polarized light, the substance rotates the plane polarized light towards clockwise direction is nothing but what it is? Dextro-rotatory substance. In the same way, if it rotates on the anti-clockwise direction, we can say that it is levo-rotatory substances. So now we discuss Sn2 mechanism and Sn1 mechanism. In Sn2 mechanism, start first. So the optically active alkyl halides as a result of stereochemistry or stereochemical aspects. In the same way, Sn2 mechanism also, the substance, whatever the form, the compound carbocation, it is also optically active halide because the asymmetric carbon. Asymmetric carbon or chiral carbon is nothing but which has four different groups. So the product formed as a result of Sn2 mechanism is inversion configuration. Why it is inversion configuration is nothing but because the incoming nucleophile attacks exactly on the opposite side of the halogen occupied in the previous molecule. It is exactly attacks on the opposite of the halogen present in the molecule. So example for this one, when means the negative means levo. When levo-rotatory 2-bromo-octane reacts with any of its molecules to form dextro-molecule of 2-octane 2-ol. This is the best example for Sn2 mechanism. In this case here, this pair is the position of the front side of the carbon. Now, this halide, the nucleophile attacks exactly opposite side of the halogen present in that carbon. So we can say that it is inversion configuration. If the nucleophile attacks at the same position of the halogen, it is called as retention configuration. If it attacks on the opposite side of the halogen, we can say that it is inversion configuration. So in the same way, now we move on to Sn1 mechanism. We conclude that Sn2 mechanism undergoes whose configuration? Inversion configuration. Now we move on to Sn1 mechanism. Same in the case of optically active alkyl halide. In the case of optically active halide, Sn1 mechanism undergoes which kind of configuration? It undergoes racemization. What is mean by racemization? I said that retention plus inversion gives rise to racemization. What is mean by retention? If the incoming nucleophile attacks at the same position of the halogen, we can say that retention. If the incoming nucleophile attacks at the opposite side of the carbon means halogen, we can say that inversion. This is the inversion because this halogen is turned this side. It is attacks at the exactly opposite of the halogen called as inversion. This is retention. Retention plus inversion gives us to what? Racemization. So in Sn1 mechanism, whatever the formation of carbocation is formed, that undergoes what? Which hybridization? sp2 hybridization. How can say that sp2 hybridization? Say how many sigma bonds are there? 1, 2, 3. 3 sigma bond means what? sp2 hybridization. 4 sigma bond is nothing but what? sp3 hybridization. 2 sigma bond means sp hybridization. So whatever the incoming nucleophile attacks in Sn1 mechanism, it attacks on the either side of the carbocation. It is either front side or else it is back side. As a result, the product is undergoes which one? Racemization. Example for this one we discussed that 2-bromobutane. What is that? 2-bromobutane pairs on hydrolysis, you will get plus or minus dextro. Both dextro and levo of 2-butane 2-ol. This is the best example for Sn1 mechanism. This is about Sn2 and Sn1 stereochemical aspects for your syllabus. If they ask for 3 marks, you can explain both the up to your right response.